Hi, and welcome to this video where I'm going to explain how to calculate the distance between 2 points in three-dimensional space. I'm going to talk a little bit of where that comes from and how we can use the Pythagorean Theorem to make that operation. And then I'm going to implement that in C#. I'm going to show you how to write the function that is able to give you that distance between those 2 points. And I'm going to be doing this in C# inside of Grasshopper, which is an algorithmic modeling software for 3D modeling. Okay. However, this implementation, even though I'm going to be doing it with this particular software, I'm not going to be using anything that is outside of the plain C# world. So you could bring this implementation perfectly into any other language like Python, JavaScript, C++, or whatever you want to do. Also, the algorithm that we're going to describe will work exactly the same if what you want to do is to calculate the length of a line segment, or if you want to calculate the length of a vector. All right, so join me and let's get started. The first thing we're going to do is we're going to talk a little bit about what calculating the distance between 2 points means geometrically and in Euclidean space, and then what technique we can use to do that. So what you can see in this really bad sketch that I just drew is we have 2 points in space. I'm going to start describing this in 2 dimensions. We have 2 points in somewhere in space, in a coordinate system that has an x and y direction, right? And then each one of these 2 points is going to have x and y coordinates. Now, what we want to do is we want to calculate the distance between 2 points. And that distance, in practical terms, is equal to calculating the length of an imaginary line that would join them one to the other. Okay, so how can we do that? In order to do that, we're actually going to be using some really ancient trigonometry and ancient geometry principle. And the one that we're going to be using is the Pythagorean Theorem. I never know how to pronounce that, sorry. But this is a principle that explains that for any triangle in two-dimensional space or three-dimensional space, if the triangle has one of the angles is square, so one of these angles is 90 degrees, then the relation between the lengths of the three sides of this triangle is equal to this formula that we have here. The square length of one of the short sides plus the square length of another one of the short sides equals the squared length of the longer side. This theorem has very often been illustrated by adding the areas of the A and B. So adding the areas of the length of A and B and how they add together to the area of C squared. But in terms of three-dimensional geometry, it's very simple to see the relation of this theorem to how this works out in 3D. So here, in this line, we can imagine that given 2 points in space, we can trace an imaginary triangle between them that has, with the long side being the distance that we actually want to calculate, and then the short sides being the straight line, a horizontal line in the x direction starting from A, and the other short side of the triangle being a vertical line that starting at B, and both of them joining in some point in three-dimensional space and forming a 90-degree angles, because the two axes of the coordinate system form a 90-degree angle. So if we label these three sides of the triangle, A and B being the short ones, the ones that are parallel to the coordinate system, and C being the line that joins these 2 points, then the problem is just as simple as calculating the distance, the length of C, based on the lengths of A and B. And the thing is, because we have the coordinates of A and B, for us it's going to be very simple to calculate the lengths of A and B, and then therefore just apply this formula here. So how would that work? If we know from the Pythagorean theorem that that C squared equals A squared plus B squared, then we can elaborate a bit more on that by saying, well, here, if I rename these variables, if I rename them distance in the x direction, if I rename this side distance in the y direction, and if I rename this side here d, then this problem, now becomes the distance that we're trying to find equals the square of the distance in the x direction plus the square of the distance in the y direction. Does that make sense? And interestingly, for us, it's very easy to see that the distance dx, I'm going to write it here, dx is going to be equal to whatever the coordinate, the x coordinate of b is, minus whatever the x coordinate of a is. And dy is going to be equal to whatever the y coordinate of b is minus whatever the a coordinate, the y coordinate of a is. So if I plug these two in here, now what I get is that distance d squared equals bx minus ax squared plus by minus ay squared. And if what I'm trying to find is this value, then the only thing that is left for me to do is to say, well, now all of this is just equal to d is equal to the square root of everything that I just described. Bx minus ax squared plus by minus ay squared. And this is the formulation that I need to do in order to find the distance between those 2 points in two-dimensional space. What we need to note here is that I know the x-coordinate of the point B, I know the x-coordinate of point A, I know the y-coordinate of point B, and I know the y-coordinate of point A. So because I know all those values, then I can calculate this distance. So we just solved this problem for 2 dimensions. Is that clear? Now, how does this extend to 3 dimensions? Well, it just so happens that the Pythagorean theorem, it works exactly, you see, here, this is what I just described. And here, this is exactly the formulation that we just described as well. It's just that this notation is inverting, this one is A and this one is B. Oops, sorry. Sorry. So here you can see that I'm using this link. Here they're describing the exact same problem. They're using like a slightly different notation. Here, A is the point on the right and B is the point on the left. So this notation is slightly different, but they reached the same result here. And what's interesting is that this notion also extends to 3 dimensions just equally. So if I go back to my drawing board, I can turn this off, and you can see it's very easy to demonstrate that that if we had this in 3-dimensional space, then it's just also as easy as saying the distance between those 2 points is going to be equal to bx minus ax squared plus by minus ay squared plus the c coordinate bc minus ac squared. Just as simple as that. Okay, so this is what we're going to implement today. And it's going to be like a super easy numerical rule to do. So let's go ahead and take a look how that works code-wise, okay? Wonderful. Let's take a look at how we would implement that. So what you can see here is that I have created 2 points in Rhino. Those 2 points, I can move them in 3-dimensional space. And then in Grasshopper, I have taken these points and I have imported them. And now we have them as entities in Grasshopper. And I'm using this Grasshopper component called distance between 2 points, just to verify that the algorithm that we write is going to work well. But we're going to implement our own algorithm from scratch. You can see that what's interesting about this is that whenever I move the points in three-dimensional space in my modeling software, the value of the distance updates here on the visual program, on the algorithmic modeling software. So I think that's a really good start. Then what we're going to do is, in order to write our own implementation, I'm going to create a C# scripting component that I'm going to be able to customize inside. The first thing that I'm going to do is I'm going to rename the inputs. I'm going to say this is going to be A and this is going to be B, just to mimic this component here. And then the output is going to be D. I'm going to plug in the 2 points that I'm bringing in from my 3D modeling environment. And then, very important, I need to right click on each one of the inputs and make sure that I force each one of these inputs for the function to be 0.3D objects. So that when I double click in the function, they show up in my main function here as 3.3D objects, and then I can have access to their X, Y, Z properties. Okay, if you are we're going to be implementing this in C#, but if you're we're going to be using part of what's called the Rhino common library, which is a geometry kernel that has a lot of geometric entity objects. But if you're writing this in some other environment where you don't have access to a geometry kernel, it's perfectly fine, so long as you create some kind of class that you can use as to represent a point, and something that just has X, Y, Z properties. That's totally fine. And even if you want to create your own function where you break these arguments apart into simple X, Y, Z for the first point and X, Y, Z for the second point, that's also absolutely fine. Okay? All right, so we are here. And then what I would like to do is I would like to create my own function that I'm going to call distance between points. So, and because what that is going to return is a value, is a number, so I'm going to say that the return type is going to be double. The name is going to be distance, and then it's going to be distance, for example. Yep. And then here, one of my inputs is going to be a 0.3D object called A, and then the other input is going to be a 0.3D object called B. Just as simple as that. And then, as per our diagram, remember that we discussed how, for example, here. We discussed that the sides of each one of the triangles are basically the difference between the X and the Y coordinates of the 2 points. So we're just going to implement that same logic here inside of our function. So what I'm going to go do here is I'm going to create a variable called dx, and this is going to be equal to b dot x, so the x coordinate of the b point, minus a point x, and I'm going to mimic this for y and for z. And remember, copy pasting is the devil. So if you can write these things on your own, that is probably a much better way to do things, because copy pasting just yields a lot of errors. Calculate the sides of the triangle. Okay, and then here I'm going to calculate the length. Calculate the length of the larger side of the triangle. And then, so here I'm going to say double D, and I'm going to go back to the diagram. Remember, D is going to be equal to this side here, which is dx squared. Sorry, actually this should not be here, this should be here. Exactly, sorry. And then plus the dy squared plus dz squared. So I'm going to go here and say d is going to be equal to dx squared, or dx times dx is the same thing. This is much easier and much faster to compute for the computer. and then dc times dc. But remember that all of this was inside of a square root. So let's see, we need to wrap this inside of a square root. So that's going to be through the math object. We're going to calculate the square root, and then we're going to open parentheses, and then we're going to close parentheses here. And then this is the value that we're going to return for the main to the main code. So now that we're here, now we can say, for example, in order to run this function, we can say calculate v as the distance between point A and point B, and output this. This is going to be perform calculation, and this is going to be output it through the component. And as I do this, if I run this code now, if things are going well, and then if I click here, you can see that the result that I get is exactly the same. And I'm going to double test this. If I move this around, if I move any of the points around, both values update synchronously. So it looks like this is working well. So yep, so this is how you implement calculate the distance between 2 points. It's very simple. All right. I would like to make a reminder here, and conceptually, what we've done here is to calculate the distance between 2 points, but in practical terms, this algorithm works exactly the same if we also wanted to calculate the length of a line segment, because at the end of the day, a line segment is basically the line that we draw between 2 points. So if we have the coordinates of those two ends, then we can apply the same logic. And also, this algorithm is also the one that is used for calculating the length of a vector. Because remember that vectors are represented by the x, y, z coordinates of where the tip of the vector is. So in practical terms, if we calculate the distance between that point, the tip of the arrow, and 0, 0, 0, then that is the length of a vector, right? So this algorithm would be the same as calculating this minus 0, minus 0, and minus 0, or a point B being at 0, 0, 0. All right? So that's good. So, but before we move on, I want to also explain how to do another operation that is very, very common in computer programming, and especially when we do geometry calculations, and that's going to be calculating the squared distance. And let me explain why I want to do that. The reason we're going to implement this thing called square distance is because when you're calculating the distance between 2 points, we're using the square root of a value. And the square root of a value is an operation that is not very expensive, but is definitely much more expensive than just simple additions or simple multiplications. So if we're writing an algorithm that is going to require calculating the distance between thousands, if not millions of points, then having a square root as part of the algorithm may actually make things a little slower. So there will be times where we just cannot avoid that because we actually need to calculate that distance because that's the value that we need to do. But there might be algorithms where which work by comparing points between them. And sometimes what you want to do is you want to compare those distances to see which points are closer to each other or something like that. And in that case, the value of the distance itself is not that important because what's important is the relative differences between distances and between different points. So when that is the case, then it's actually much cheaper to compare distances between points by, instead of comparing regular distances, by comparing what's called their square distances. Okay, and this sounds a little complicated, but I'm going to record another geometry gem next to this one, where we're going to clean up lists of points that may have duplicates, and then the square distance is going to be very useful for us in that case. Okay, but in this case, we don't really need this because we're actually calculating the straight distance between these 2 points. But if we were to compare this distance with the distance to other points, that would be a much more interesting and much more optimized function to use. Okay, so I'm not going to show that on this video, and I'm going to invite you to join me for the next one, the next geometry jam, where I'm going to remove duplicate points from a list, and then in that case you will see how using the square distance will yield us and will give us a much faster algorithm than just using the normal one. Okay, so I hope this was useful, and join us for the next geometry jam where we see a real world implementation of these techniques. Okay, thank you very much.